Alright, hi and welcome ladies and gentlemen. Today we are talking about part 2 of the AVL tree, which will be the final part. As usual, you will find the source code in my Git repository. The link is down in the description below. Okay, let's make a small recap. In the last video, we created a class AVL tree that has a node, and that node stores the values left, the right node, and the height for the left subtree and the height for the right subtree. And then we created an insert method that inserts the current value depending on where we have to go in the binary search tree. Then we wrote a method that is called Adaption, which will create which will adapt the height in the whole tree from the root tree on, and then we made a little print method that prints the tree, and if we run that, it looks like this. So we have our input as 1, 2, 3, 4, 5, 6, and we have then our binary search tree at the moment as 6, 5, 4, 3, 2, 1. Now we have to convert this binary search tree to an AVL tree. So for that, I want to start first by renaming the method AdaptHeight because we are going to do some optimization there. We will store the trace where we went when we insert a node and just update the height of these nodes. So at first, I create here this method, or I rename this method to AdaptHeight. We will still need it because we don't make this optimization everywhere, and I just rename it everywhere so that this recursion here is also called on this method. And then I want to go in here, and here we call self-AdaptHeight, and I want just comment that out for a second, and I say here AdaptHeight of our trace. For that trace, I will create a new list here called trace, and I initialize it empty. Alright, so now that we have this trace, we have to fill it. And there we can say right here, before we create a new node, or before we insert the node, that we end at our current node that we use to insert the value below. We want to add that to our trace. So here we say trace.append and we say current node. Alright, so now we have our trace. And then we can do the first optimization here when we check whether we want to insert a node in the left or the right side. The trick is here, if we insert a node to the left of the current node and there is already a node to the right, meaning the left subtree doesn't exist but the right exists, so we don't have to update the height there. So we say here if current node dot right is equal to, or is not equal to none, then we can reset our trace. And we can do exactly the same just for the left side down here where we create a node on the right. So here we can say if the subtree on the left side exists, then we don't have to follow the trace at all. Alright, then we can go in here and where we adapt our trace, we say if our trace has just one element and that is the current element, so we say if the length of the trace is greater than 2, then we say self.AdaptHeight. And this we call with our trace. Alright, So I want to add one little thing here in our insertion or creation of the node. And here I say, when we create a new node there on this side, then we also can already say that current node dot height left is equal to 1. And we can do the same with the height right down here. Because we create a new node there, so the height of the left subtree of this will be 1. Alright, so good so far. Let us create the method adapt height. We do that right here, where we say def adapt height, and there we get our trace. With this trace we want to go up now the whole trace and just increase the height of the trace on all those nodes. So we say here adapt the height of the nodes in the trace if necessary. If necessary means if we extend or if we increase the height through inserting an element, then we have to update it. But we also have to have a look, is the left subtree now bigger than the right one or the other way around? Then we want to go through. So at first I say height is equal to, no, we don't need the height actually. Let's say we go the trace reverse, because I want to start at the end of the trace, which gives me the last node we inserted there. Then I say node equals trace, and there we take element 0 out. With that we take the last element we inserted out of the trace, and then we can say trace equals trace, and there we say 1 to the end. Alright, so we have now our last inserted element, that is current node, and under this current node we created a new leaf node. So we go in now and say for, and this I call just TMP, in trace we want to figure out the maximum of the height of the left subtree and the maximum of the height of the right subtree. So we can say here max height equals to maximum, and now we have to check the left and the right height of our subtree. So node height left, and there we can already say +1, because we are looking now one layer higher in our tree. Node dot height right +1. And then we can say if our node equals to the left node of our TMP node. So basically meaning, is our node the left child of TMP or the right child of TMP, because we have to set the right or the left height of these nodes. So we can say here, is this TMP.left? Then we adapt the height TMP.height left equals to our max height. Otherwise, it is the right subnode of TMP, so we can say TMP.height right in this case equals to max height. Alright, and then we go in here and say our node equals to TMP, because we want to go up layer by layer in the tree until we are at the root tree. We could also even optimize this further in that way that if the maximum height doesn't change, we can stop there, but I want to keep it here simple now and we leave it as it is. Alright, so now we can adapt our height along our trace, and we will do that here. So let's test this out and check if that works properly. So we call here our self.adapt trace, adapt height. And if I call this now, we should get exactly the same output as before. So here we forgot to insert our self property. So if we run that now, we see that the height was successfully updated along the trace. Alright, the next part that we have to do is to check if our height is, if our height is, or height difference is greater than 2, because then we have to do a rotation. For that, I want to create a method, and I call that checkHeight. Def checkHeight, and here with a capital H, checkHeight, and that will go through our tree from the root node on in the tree and check if the height changed. So that also needs a self property. And here we say checks if the height in the subtree is imbalanced. Or also we could say if the height difference is greater than 1 somewhere. So we want to start with our root, so we say here's our q equals 2, and then we take our root, and then we go in and say while our q is not empty, so we can also say while the length of our q is greater than 0, we take the first element of our q, we call this current node equals q0, and then we check the left and the right subtree of our node. And then we say here if, and there we can use the absolute method of our Python library. So we say apps, and here we say current node dot height left minus current node dot height right, and this will be greater than 1 if there is an imbalance in the tree. So then we can say we return here the current node, and that also says us that there is an imbalance, and if we don't return anything, or if we return none, then we don't have an imbalance. So we can say here return none. Alright, so what we have to do now is also insert our children of the current node. So here we say if current node dot right is not equal to none, then we insert it in front of all the other elements in our queue. So we say here current node dot right, and that with that we create basically a depth first search. Okay, and then we want to do the same for our left node. And there we insert that also in our queue at first, or in the first position. And that finalizes our depth first search. And there we check then for each of the nodes down to the bottom if there is a height difference. Alright. So good so far. Now we can check the height of our tree. And that we will do up in our insert method. So we are here in insert and we say here adapt our height, and as a next step we check node, or we say node equals self dot, and we check our height. And if there comes something back, then we have an imbalance. And we say here rotation for weight balancing. Alright, and if the node here is equal to none, or is not equal to none, then we have to do our weight balancing. And then we can say here self dot rotate, and we do it on our node. Alright, so let's create this rotate method. For that I go in here and say def rotate, and we get our self attribute and our node. And we will say here checks what, or invokes the, and there we have to decide, do we what weight balancing do we have? Is it right heavy? Is it left heavy? And so on. And there we can say that here we invoke the balancing method for the tree. So let's start with a right heavy node. There we say node is right heavy. And we say if node dot height left minus node dot height right is smaller than 1. So basically meaning our right height is higher than our left height. Then we have to check if the middle subtree, so the left subtree of our right child, is longer than our right subtree. So here we say node is right heavy. If it is right heavy, then a single rotation is enough. So we say here if node dot right dot height left, and here we need a capital L minus, or is smaller than node dot right dot height right. So that is the comparison between the two heights of the subtrees of our right child, because our tree is there right heavy. Then we call a method called single rotation left, which solves our imbalance in this case. Otherwise, we say node is right left heavy. And there we have to invoke the double rotation, and that will be a right left rotation. So we say here self dot double rotation, and that is right left, and we also call that on our node. And now we have to do exactly the same for our left side. So else, and now I copy all of that here and put it down here. And we want to say here that our node is now left heavy. So we go in here in this case and say node is left heavy if node dot left dot the height height of the left subtree is greater than node.right.height right. And here we have to do node.left.height right. Alright, then we do a single rotation to the right. And then we are done. Otherwise, the node is, and here we say left right heavy. Basically meaning that we go, the left child of our node is right heavy. So we have to invoke here not right left, we have to invoke left right on our node. Alright, so let's go in and create the rotation methods. For these I want to create at first the single rotation left. So def, and there we say single rotation left, and that gets self and our node. And here we say performs a single left rotation. Alright, so how are we going to do that? At first we need the predecessor of our current node, because we have to set the right child of our predecessor to the right node of our current node. So we want our predecessor, and that equals save dot, and we call this method find predecessor, and we call that on our current node. Alright, so let's create the method find predecessor. Def find predecessor of our, and we get self and node. And there we say returns the predecessor of our current, of our node. Alright, so good so far, and we can implement that in many ways. In this case I want to implement that recursively over a depth first search. So we go in here and say return, and we want to call self find predecessor recursive of the node. And we want to start actually here with our root node, so self root and our root node. Okay, let's create the recursive version. Def find predecessor recursive, and that gets a node or the current node in that we check and our node that we want to find. And there we say if current node dot left equals to our node, or, and there I want a new line, current node dot right equals to our node, then we can return our current node. Otherwise, we have to check, is our left node maybe none? So if current node dot left equals to none, then we want, just if it's not none, then we want to go in and also check if the left child of our current node has maybe as a child our node. So we call here self dot find predecessor recursive of our and there we say current node dot left and node. And also if our current node dot right is not none, we also check it there. So we say self dot find predecessor, and there we say, and here we have to call the recursive version current node dot right on and our node. So what is happening here? We go down, and if we find our node, we return it, and we will return that all the time. So here is also the self missing. So we go in and we always check new ones, and if we find it, then return it, and we need to return it here too. Alright, so good so far. Let's go in and keep working on our actual single rotation left now. So now that we have our predecessor, we need to set, since we are right heavy, at first the right left node that will be the child of our current node later. So we say tmp equals node dot right dot left, and we say our current node equals to node dot right. So what we are going to do now is we set our current node as the right child of our node, because we perform a left rotation, and the predecessor and the the normal node that where the imbalance occurred, that will be the left child of our current node. So it will be then the left child of its previous right child, and the temporary node will be the right child of the node where the imbalance occurred. Okay, so we check here if our node equals to our root, and that can happen, and then we have to change our root. So we say self dot root equals to, and we need to use the two underscores again, our current node. And otherwise we have to check if our predecessor, so we have to actually set the predecessor there, or the child of the predecessor, and we can do that if predecessor dot right equals node, then we say predecessor dot right equals now our current node. Otherwise we say predecessor dot left is our current node. Okay, so good so far, and that means that we are done there, or almost done. What we have to do now is we have to set the left child of our current node to its previous parent node, which is the node where the imbalance occurred. So we say here current node dot left equals node, and then we also have to say node dot right equals tmp, which was our left child of the right node. And then we also have to go in and reassign all the weights in our tree, because we changed the children around. We can obviously optimize that, but I want to leave that for you actually. If you want to optimize it, go ahead, or if you want to see that I optimize it in another video, then yeah, give me a hint down in the comments below and say, hey, show me the optimization please. Here I write optimization possible. Alright, and then I say self.adapt hide all. I actually call this on our root. So we go there through the wall tree and set the height of our wall tree. We could change that a little bit, that we have a trace again and just set the heights of our trace. Okay, so that is the left rotation. Now we can take this wall yoke, because the right rotation is kind of similar. So we go in and say single rotation right here. And here we have performs a single right rotation. And we want again our predecessor, and our temporary node is now the left dot right of our current node, and our current node is node dot left. And here we set this again, that stays all the same. And here we just have to say current node dot right equals node, and here we have to say node dot left equals our temporary node. So we are done with our rotation. Let's do the double rotation now. And the double rotation is just a rotation of a single rotation right and then a single rotation left, or a single rotation left and then a single rotation right. But there's one little speciality. But let's create the methods first. Def double rotation right left, and we have self and our node. Okay, and we can say here performs a right left rotation. So what does it mean? We make a left rotation on our right rotation on our child node, and then we make a left rotation of our node where the imbalance occurred. And I see here that I also have to adapt that here with a double rotation, and I have to say here that is actually node.child. And we have to use the right one here, and we have to use the left one here. This is because we are right heavy in the uppercase here, so we have to perform a right rotation. We are left heavy on our right child of our node, and so we have to perform a right rotation there to bring it to the form that we can do a left rotation again. Alright, so we say here self dot, oh no, this is not here. I was a little bit confused there. We have to create here at first the right rotation. So we do a single rotation right, and this we have to do on our child node, and then we perform a single rotation left on our real node. Alright, and that is our double rotation. So let's go in and do the same for our left-right rotation. So here this will be left-right, and the other one here we have to do a single rotation left now on node.left, and here we have to do a single rotation right on our node. Okay, that was a lot. Let us put this now into our class here. This is already fine. I can remove this height adaptation now. And let's see if that works out. That should already be it. So if we run that now, that should create our AVL tree. Alright, it seems like I have an endless loop somewhere in here. And I have here a while loop in our check height method. And I also have to remove the first element there from our queue, the element that we just took out, because we are done with working on it. So I say here queue equals, and there we take the first element out, and then we should be fine. Alright, and we are still in an infinity loop somewhere, so let's see where that occurs. Here we insert it, and then we remove that. We insert these, and here we don't take the current node. We actually have to put in the current node left. And that looks almost good. So we already put in some values now, but the result doesn't look so great. So where is the mistake now? Alright, there I'm back and I found the mistake, and that is here in our single rotation left and single rotation right method. There we have here an equal sign and two equal signs, and these should be one equal sign. And when we do that, when we correct that, our program works completely fine. So let's run that. And as you see, we get as a value the 4, 2, 5, and the 1 and 3 as a child of the 2, and the 6 as a right child of the 5, and that works completely fine. Alright, ladies and gentlemen, let me take out here a few comments. And we still print a lot of our tree, so here we can remove also this one. And let's see if we have more in it. No, that looks fine now. Alright, that was it for that video. If you liked it, give it a thumbs up. I hope it helped you. Post down in the comments below what you think about the video. Now at the end I also link the video of the first AVL part, so that you can also check out the theory and the generation of the binary search tree that is needed for the AVL tree. Alright, have a great day and we see each other soon. Bye!